So the thing is that the last step, amplitude analysis, is something that really not too many people in the collaboration are actively using at the moment. And I thought that it would be a really good idea if Colin would explain what he does, because he's one of the very few people that actually uses AMP tools on data from GlueX. And he made a few nice slides, but then unfortunately he was too sick to come in today. And I don't know what we are going to do. Just together we can probably figure out what he meant by the slides.
Okay. So the group effort.
Right. So he's working on a channel which has an eta and a charge pion recoiling against the delta plus, which decays into a proton and a pi plus. And he's basing his talk on this example. He has a few disclaimers. Using AMP tools is simple, but so it's basically just running one line, but getting the right results and putting everything together is complicated. And here is really something that some development is still needed from our side, and we have started this, but since the user base is not too big at the moment in GlueX, it's really at the beginning, and you will see this. There are many open questions, open points at the moment, where a lot of nicer tools could be added. I should continue.
Do you want me to? I could try to give his talk.
Okay,
See what happens. Yeah.
Do it.
Okay. All right.
Do it. Just tell me.
So this is the second time I've looked at the slides. So
you have a
great
remote.
Excellent. Whoops, wrong button. Yeah, right. So Colin's looking at this channel. Gamma P goes to eta pi minus delta plus plus. And he's going to show in the slides there's a Mach amplitude analysis of the eta pi minus system. So the idea here is that this is charge exchange production, and the delta plus plus is just kind of along for the ride. Well, it's the recoil particle. So we're not doing any sort of analysis on the delta plus plus decay or anything like that, just looking at the eta pi system. So in principle, this analysis could get much more complicated. The beginning also doesn't take into account the photon polarization. So it's like unpolarized production of eta pi at the very beginning. And so it's just the first stages of trying to get this thing working. So let's see. Lots of steps of modification need to be made to get to the end. Also need, right, you see some notes here. Okay, so that's it. We're done. So fit is the code that actually runs the fit from AMP tools. There are examples of this. I think this is part of the GlueX repository. So just to remind people, AMP tools is a general purpose library that contains basically no physics and knows nothing about the GlueX detector or data format. So all AMP tools knows about is likelihood fitting, basically. And so in constructing intensities and things like that, which have notions of quantum mechanics. And so what we as GlueX users of AMP tools need to do is we need to develop a library set that has physics, amplitudes, and also information about our data format and those sorts of things. And we ask to write the executables that use AMP tools. And so fit is one of those that does that. It's in there. So what does AMP tools need? It needs several things. So the first two files are needed to do an acceptance correction, right? So the idea of all these fits is that you are looking at the angular distributions of decays, and depending on what the angular distributions look like, you can learn something about the model or the spin of the particles that are produced and these sorts of things. Well, you want to make sure that the effects you're seeing are actually effects due to physics and not due to detector acceptance, because detector acceptance will also modify the observed angular distributions of particles, because the detector is not perfect. And so what AMP tools does is AMP tools actually tries to match the data to what is some physics model times the detector acceptance. And to do that, you have to tell the package a little bit about what the acceptance is. And so it does that by really the key thing in that is just this accepted Monte Carlo. So the input is important for overall normalization, but the accepted Monte Carlo is Monte Carlo that gets generated that is flat in all the physics variables you want to study, so things that have no physics effects. And then it's passed through Géant, it's passed through your reaction filter and all of your analysis cuts in the end, and that carves it up according to the acceptance of your analysis. And then what happens is you take this thing times some physics model and try to match it to what the data are, and that's the goal of AmpTools. And the physics models define them by this config file down here. And typically when this is done, well, this can be done in a variety of ways. Are you raising your hand, or are you just stretching?
Oh, no.
Oh, okay.
No.
Okay.
I just scratched my head.
So you can define the model in a variety of ways. You can imagine having a Dallas plot, for example, and you want to fit all the data on the Dallas plot. What Colin's going to do in this case is he's doing fits where he takes the eta pi system and he carves it up into bins that are basically fixed in eta pi mass. You just take a little small range of eta pi mass, and then you try to look at the various components in the eta pi system. So, and when you do that, the only thing that matters basically are two angles. You have this eta pi system gets produced, and the things that you care about are and eta and pi are both spinless, so there's no information there at all. So it's just when the eta pi system decays, it's those particular angles are all that matter. Okay, so he has some instructions here, I think, about what to do, and the examples are there. Let's see, overall there's some pieces. Let's see, copy files to directory, you want them to go. That seems pretty clear. Then you have the data that have to get divided up into all these bins of eta pi mass, and then you need to do a fit in each individual bin, and then collect all the results from all those fits and analyze them. I think there's a picture here. Yeah, right, great. So imagine that you collect some eta pi data with GlueX, and you plot the eta pi invariant mass. You may get a plot that looks something like this in the bottom right picture. Maybe it has some peaks in it. And so this is some toy data or pseudo data that's generated with a fake, an A0 wave here. So this is a spin 0 peak and an A2, a spin 2 peak. And then you can try to analyze this and see that you extract these pieces. And the way that Colin does this fit is that he first takes the data and then divides it up into all these bins. So basically, if you were to look at the dot here at 1 GeV, the dot here at 1 GeV, and the dot here at 1 GeV, 1 GeV, 1 GeV, those are all parameters to one fit for the data that are right around 1 GeV. So you do one fit right around 1 GeV, and you determine the relative amounts of S, P, D wave, amplitude, and then you go to the next bin and do an independent fit in that bin, and then you go to the next bin and do an independent fit in that bin. And then you collect all the fit results and plot, say, just the S wave amplitude as a function of mass. You can see it actually traces out a little bump. So you've separated out this bump here. And in doing that fit, you make no assumptions that this is a bright Wigner, for example, or anything. You're just trying to pick out the S wave piece of this, and you see you can separate out the D wave piece. So here's the nice thing: you can separate S and D wave. And so this is kind of the answer in the end. This is Colin's test. This is using toy data, not with real data. So in some ways, this is cheating a little bit because if you go back to what Justin was saying, so one thing that's really important is that the Monte Carlo models the acceptance of the data. And what Colin has done here is Colin has generated some fake data and then passed it through the Monte Carlo. And then he has this flat phase-space data that's used to do the acceptance correction, but it gets passed through exactly the same Monte Carlo. So, because the Monte Carlo is exactly the same in both cases, they're almost guaranteed to agree. In real life, we can't do that. Of course, we have to have the data, but then the Monte Carlo has to match the data. Okay, so input. So what are these various components that go into the fit? One is this flat Monte Carlo, and so here he is describing how he generates that flat Monte Carlo. And now we have a little bit of a limitation with our Monte Carlo generators, and that's that we don't have a really good way to put a resonance at the lower vertex. And so what Colin has in his channel is the eta pi system going out, but then you have a wide delta plus plus that decays to proton pi plus. And our generating system is not general enough to allow complications at the upper vertex and the lower vertex at the same time. And so what Colin does to get around that a little bit is that he uses some of the features of amp tools to carve a Breit-Wigner out of the lower vertex. So what he does is he's generating eta pi pi, but he's basically doing accept reject on a delta Breit-Wigner at the lower vertex. So that guarantees he's going to get this nice line shape, for the delta plus plus the lower vertex. And the upper vertex, which has eta pi minus, is going to be flat. And so that's what this is. This is that delta Breit-Wigner. This stuff is not so relevant, I think. This is basically just defining the parameters of the delta that gets used as arguments to the Breit-Wigner class. And this tells you which particles the delta is. And then Thomas can tell you about what the first line means, probably. I think
all of these.
This is like the lower end of the mass range, the upper end of the mass range. This is maybe a beam energy range, yeah.
So in all the amp tool style generators, a lot of them had various command line options.
Right.
And to unify them, all I do is I take that top line, I reserve that top line with the pound sign.
Right.
And everything to the right of that commented out sign doesn't get interpreted by the amp tools generator. But MC Wrapper will copy that string and put it in the call.
Right. So if you want to know how to read this part of the file, this is defined in the amp tools reference manual, which is under development. All these queries. Okay. So the output of that is the following. So this is the output of the generator. So this is before it goes to the detector. So what you have is something. So this is the eta. I wonder if this is a typo. It should be, I think, eta pi invariant mass. No, it could be eta pi pi. I don't know. Yeah, it looks like it starts at eta pi pi threshold.
Are usually pre-populated by the code. So.
Yeah, right. Okay. So anyway, it's flat there. Here's the. That's definitely wrong. Pi pi plus. So that should be, I think, proton pi plus. That's the delta plus plus peak. And you see that it's flat in angles. There's no physics in any of the angular variables. And so this is what you would take this Monte Carlo. This is the physics-free Monte Carlo. Pass it through your through Géant, through your deselector or whatever analysis cut you're going to make, and then take everything that you do to the data you do to this particular file, and then you pass that back into amp tools for a fit. So then, I guess in the end, amp tools uses yet another slightly different format for a data file, so it's kind of like a flat tree format. Again, this is not really specified by amp tools. One of the things that users of amp tools provide is a class called a data reader. So we could make amp tools read in HDDM if we wanted, or XML or anything. We're free to specify this format, so we should do it in a way that's convenient for us and convenient for everybody else. But right now, I think the standard that people use is that the beam 4 vectors are given by this, and the final state particles. So these are like variable length arrays. Well, actually, every event has the same number of final state particles as fixed length arrays. But these are arrays of the final state particles, and the file or the data reader for amp tools reads that file in. Right. So then this is what happens to the accepted Monte Carlo. Why does this say data time? Pass generated 4 vectors through the detector simulation, subject them to the same cut you make on data. All right, good. Need to. Bert?
This efficiency?
Yeah, I think it's the reconstructed Monte Carlo. It's not data.
Yeah, I think that's right. I think this is the reconstructed Monte Carlo times.
But the efficiency.
This is the generated. And this is the reconstructed.
The efficiency is only 3%, so
right.
He has to multiply it by 20 to
make it visible. To make it visible, yeah, right. So when you so you can see that's right. So this is the generated shape of the eta pi invariant mass, and then this is the reconstructed shape. This is one of those key angular variables that you're going to look at to analyze the spin of the eta pi system, and it's generated perfectly flat. But this is what our detector does to that variable. In the analysis, you see it introduces some shape to it that's non-trivial. And so these shapes have to be accounted for when one goes to fit the data. or else you're going to find all sorts of false waves that generate this. Right, so this is the accepted Monte Carlo. And then this, oh, right. So how do you get the data? So here is how you would get the data if you're using real data. You would run the deselector over analysis trees, and then you would make this flat AmpTools file, and then pass it into AmpTools. What Colin does for this tutorial is he generates fake data by using AmpTools to generate interfering money or generate some physics basically. And so then here is the configuration file that's used to generate. Remember, there was an A0 and an S wave, that's A0980, and A21320 and a D wave. And how you specify what those resonances are is given by this little incantation here. So we can go through this, maybe it's useful. So this defines an amplitude in AmpTools. So the AmpTools has this idea that amplitudes are factorizable. So there's one function times another function times another function. So right here, what this line says is define an amplitude for the reaction eta pi in the coherent sum negative. There's only one coherent sum here. So if there were separate polarizations or separate observable variables, you would have several coherent sums that are added together incoherently. But in this case, it's not so relevant, so you can almost ignore this because everything says negative. And here's the amplitude. So this is the S wave amplitude, and that amplitude has three factors in it. It has, first of all, the delta plus plus Breit-Wigner that describes the shape of the lower vertex. It has a A0 Breit-Wigner. The parameters of the A0 are up here, 980 and width of 100. And this tells you which particles the A0 decays into. And then the other thing that it has that's important is this this amplitude 2ps angles. So this says it's a spin zero decay. So this makes sure that it's generated flat in those key angles. And so those three factors together specify the delta plus plus dynamics, the A0 line shape, and the A0 angular distribution. And that makes up the whole A0 amplitude. And then that's repeated here for the A2 amplitude. And you see some things are a little bit different. The A2 still decays into the same eta pi, but now it's a L equals 2 decay. So that's what that 2 there means. And then here are some arguments that change the angular distribution of the A2 also. And so this is the A2 amplitude. And then, so this is basically the exact same model almost. That's not quite the same model. So when you go back to fit the data, what you're going to do is you're going to divide the data up into bins of mass, and you're going to fit for this intensity and this intensity. So what you're going to pull back out of the fit is this Breit-Wigner as a function of mass by fitting for the amount of this angular distribution and that angular distribution. Probably add a few more slides to this if I could. But all right, and so then initialize the amplitudes and then go. And I mean, what AmpTools has to do is AmpTools knows how to calculate the predicted number of events over some area of kinematics. And so what you can do is you can use that very same algorithm to generate Monte Carlo just by a simple accept reject algorithm. And that's what GenAmp does in the end. Right. So now we can go back, and this is the configuration file so this is used to generate the fake data that has physics introduced. And then you process that through the detector and the reconstruction. And then you divide it up into bins of mass. And then in every little bin of eta pi mass, if we go back to this plot, what we want to do is we want to do a fit in every single bin of eta pi mass. And so to do that fit in every bin of eta pi mass, you need a configuration file. And that configuration file has to define this amplitude, this one, this one, this one, right? And so that's what is here. You see that here's now the configuration file that gets passed in that is used to drive the fit, to actually do the fitting. So it specifies the reaction, has these coherent sums. Here are the three files, the generated Monte Carlo and the accepted Monte Carlo. And then here's the fake data file. So that's the generated data of physics, passed through the detector, passed through analysis cuts and everything. And now these are the 1, 2, 3, 4, 5, 6, 7 amplitudes, which should correspond to 1, 2, 3, 4, 5, 6, 7 amplitudes here. And so in every bin, one is extracting a complex number that corresponds to the magnitude and phase of each of these amplitudes. And that should trace out basically a Bright-Wigner A0 and a Bright-Wigner A2 and nothing else, because that's what you put in. Those were the factors that you put in here to generate the Monte Carlo in the first place. And then you have to initialize the parameters to do the fit. And there will be, one of the parameters has to be real, or else you're going to have a phase ambiguity overall, and then we will fail to converge. So that's why real here. And so then Colin does that fit in every single bin of mass, and the output of the fit is 7 complex numbers, where one of them is constrained to be real. And those complex numbers are what, or probably the magnitude of those complex numbers are what are being plotted here as a function of invariant mass. Good. So here's some details about how to divide the data up into bins of invariant mass. And so, yeah, if I remember this code right, every bin has the relevant data file for that small range of invariant mass, and there's a configuration file for that range. And so you run this fit inside of each directory that's defined for every bin. Then one can go inside of one of these bins of mass and look at the fit results. So there's some other code that is used to make plots. So this is here. And every time you run a fit, it will produce, AmpTools will produce, the fitter will produce a file called whatever you named it, bin whatever .fit. And that .fit file has everything that you'd ever want to know. It has the whole configuration file that you passed in, and then the error matrix and lots of information about the exit status of MinWi and all kinds of good stuff are in here. And so then you loop over all the bins, running this fit in every bin, and that's what this little Perl script does. You have a Python script, but Colin hasn't tested it, as I read.
I'm working on it, yes.
Yeah. And then there's, I think, a little root script that goes through, and so what one has to do is one has to pick out those key numbers out of every fit file that's in every bin. And so I think that's what this does, is a little script that goes through and picks out the amplitudes, and then another script to plot it. Or you can do other things, project moments, or whatever you'd like to do. So that's the end. That's the last slide.
I have a question.
Yeah.
So let's assume, well, in this particular case, of course, you usually put in an A0 and an A2,
Yeah.
right? So let's assume you do not know what is actually in the real data. What would happen if you would have fitted with an L0, L1, and L2? In other words, obviously you would have more amplitudes.
Yeah.
But you know what would happen when you would have done that?
With the real data?
Yeah. Well,
So we did
with this fake data,
Okay.
if you would have.
We sort of did that because if you look at this plot, oops. So we put in,
Yeah.
Colin put in, I didn't do anything. Colin put in this amplitude and that amplitude, and all these were 0. And you see the fit extracts 0.
There are. Oh,
Yeah.
okay. There is.
There are points here.
I
They're all
was-
consistent with
never mind.
0.
Okay.
Right.
Thank you.
Now, what happens in real data is that, of course, your acceptance correction is not perfect.
Right. And you have background also.
And you have background, and so all that finds its way into these other waves somehow. And so you need to make sure that they remain robust when you start turning knobs and things. Yeah.
No, if I understand now, for this to work properly for real data, if I assume for some of the channels, we got a sum over an entire run period, maybe 2 run periods, where then between runs, detectors dropped in and out, tubes were missing in the AFCA, new tubes come back. So strictly speaking, this flat Monte Carlo has to be done in proportion to all these runs where things have changed.
That's right, and we
Yeah,
have
it's all right, yeah?
we have exactly that framework to
We
do.
have a robot that does that.
We have-
for
You
us.
have a robot that does it well. Okay.
So Thomas,
That's right. No, we know that the time dependence of the detector is important. It's also important for the random, the noise too is probably time dependent too.
Yeah.
And so one has to consider all these things. And so, yeah. But it's been done before. This is people have done this. Yeah.
Any other questions?
Email Colin if you have them.
Yeah. Well, I think one of the nice things, especially about these last couple things, right, is that there are exercises on the website and everything. So, I mean, yeah. So this is really great that you could give Colin's talk, but I think a lot of it is also showing how he's going through and doing this.
It does need. I mean, what you say is correct. That this is a place where there's a fair bit of development. There's actually, I mean, even development beyond it. I mean, there's technical things like writing scripts to make it easy, but then there's intellectual things like what are the important variables. So there's JPAC has a paper in the final stage of review where they're talking about moments that incorporate polarization into a combination of eta pi moments that also account for photon polarization that are sensitive to exotic production. So there's kind of a lot of open discussion about the best way to go about analyzing this. But I think the AMTools framework is flexible enough that we can do these different things.
Yeah, what about a moment analysis?
So the
AMTools.
it can be done now in a very inefficient way, and there's a way to make it more efficient that is partially written on my laptop and not really tested yet. So that's a very high priority item. Yeah. But the SDMEs are similar to the type of fit you would do for a moment. You're burning a lot of CPU when you don't have to. But there's nothing wrong at all with the implementation right now. It wasn't written.
Okay, thanks, Matt. So the next on the schedule I see that Alex put down was a Q&A.
Oh yeah, and just in case there were any questions that came up and we didn't have time to address them during the talk, or I don't know.
Okay, so maybe I'll suggest is, first if there's any, burning questions that people had, for the speakers, or anything really important that they thought that should be addressed here. Otherwise, maybe the experts can hang around afterwards for a while, so that they can at least be available for some informal discussion. So, anything that's important for the whole group to talk about? Okay, if not, thanks everyone.
Hang around for the next 3 days.